Good afternoon, everyone. For the last time. Hooray, I hear you cry. What I thought I would do today is not re-teach you the whole module, but just introduce you to a few snapshots of stuff that we've talked about over the past few months. I don't want to give you a false impression in doing this. I don't want you to think that the only important things in this module are the things I'm going to show you today. It's not the case. Everything is important. And if you can get your head around the concepts that I've introduced you to, then so much the better for you. We are going to come back to some things again next semester, next year, in years to come, which is why we have this foundation module. But the other important thing is that I'm not sure if you know this or not, but you've got an exam. Horrifying roll of the eyes there. So this is in some way my attempt to help you, without telling you what the questions are going to be, just help you focus your studying a bit more in a better way. Rather than feel you have to learn absolutely everything, and I'll be delighted if you do, but rather than force you to try and learn absolutely everything, then I'm just going to go through some things that I think it might be better for you to spend a bit more time on if you don't understand them already. Unfortunately, all I can do for you is based on my lectures. I do not control Dr. Whiteman's lectures or Dr. Whiteman, and if he's not doing something similar, then I can't do anything about that. Has he done something similar? Has he gone over main points with you? Possibly because he's got less time with you than I've got. And I've deliberately tried to get through things, so I have this week to look at stuff and just refresh your memories about important concepts and points and information that you're more than likely going to need in a couple of weeks' time. Has Graham explained that you will get a data booklet or a couple of data sheets in the exam with you? Yep. Blank looks. You'll get a couple of data sheets in the exam with you. They will be, unless this has changed, there will be a periodic table and there will be tables of electrochemical half-cell reactions and their associated voltages. Because it would be pretty tough and a bit cruel to make you learn all these things. So you're not going to go in there totally blind. You will be given some information that will help you answer some of the questions. Unfortunately, everything else you bring with you into that exam is going to be stored up here. Okay? So, without wasting any more of our valuable time, let's have a look and see what we're going to talk about. Law of conservation of mass. What goes in must come out. We can't invent new atoms and we can't magically make atoms disappear. If we write a chemical equation with reactants in it, then we should be able to explain what's happened to every single atom in those reactants as they form products. Helps us write balanced equations, which are extremely important in chemistry, understanding the relationship between reacting substances and the products that they form. We also have the law of constant composition or definite proportions. That is, that in any chemical substance, the number and type of atoms will remain the same forever. If the number and type of atoms change, then we've changed the chemical compound. We can no longer call it what we called it before. So there's consistency. We always describe sodium chloride in the same way, for example, or glucose, or DNA. We talked a bit about atoms and some of the information relating to them. We introduced, or we possibly even just reinforced ideas about atoms and that information, in that we have an atomic number which identifies the element itself. It's the number of protons. And irrespective of how many nuclear particles there are, an atom will always be of a particular element if it has the required number of protons. Carbon will always have 6 protons, for example. Hydrogen will always have 1 proton. Mass number was the sum of all the nuclear particles, protons and neutrons. And this gave us a second way in which we can describe individual atoms of different elemental types. And of course, associated with atoms there are electrons whizzing about outside the nucleus. And in a neutral atom, the number of electrons is equal to the number of protons. It has to be. We're calling it neutral, which means it doesn't have a charge in one particular direction or another. The balance is there. It's inherent. Protons equals neutrons. No, it doesn't. Protons equals electrons. And this led us to the periodic table, which is a very nice way of laying out information about all the elements. And it's done in a particular way, and we can use this format of our description of the elements to understand certain properties, and we can understand certain trends as well. The properties that we can understand from them are related to the way in which they're laid out in columns or groups. So we can say something about the properties of, for example, the group 1 metals. They all have a common property. They all have a single valence electron. They all react in pretty much the same way. Not identically, but pretty much the same and in predictable ways. So if we know something about sodium, then we can extrapolate and say that that general set of properties will be the same generally for things like rubidium or cesium. Same with the halogens. whatever we can say about fluorine in terms of its chemical reactivity, we can extrapolate that to the others because they share common property. They have the same number of valence electrons. And if you remember when we talked about chemical reactions, not just in terms of what I was doing with you, but particularly in terms of things that Graham did with you, then it is the movement of electrons that is what's happening when a chemical reaction takes place. Bonds break and new bonds form, and it's done by the transfer of electrons. So electrons are quite important. They're the things that make it all work. We'll come back to the periodic table when we talk a bit about trends, because we can describe trends as being directional with respect to the periodic table. We also learned that we can describe the formation of chemical substances by using this idea of valence electrons. And the way in which the periodic table is laid out, then as we go along a period, then the element to the right of the previous one has another electron in its valence shell. It starts off with lithium in this particular period having 1 electron in its valence shell, all the way along to neon, which has 8 electrons in its valence shell. And this idea of a filled valence shell gives rise to what we call the octet rule, which is it's not. When you think about hydrogen and helium, we don't have 8 electrons in their outer shell, but it's a convenience to call it the octet rule because in using those words we understand what we're talking about, a filled valence shell. And how that shell becomes filled depends on the nature of the elements themselves that are reacting and the type of bond that can form. So one of the driving forces for chemical reactivity is this idea that atoms in compounds want to achieve a filled valence shell. They do it in a number of ways. They lose or they gain, or they share. And we can predict something about what they're likely to do before we get to that. We do show a couple of examples of a group 1 element losing an electron, forming a positively charged ion. Its valence shell electron has gone, so the new outer shell becomes the new valence shell, and it is filled. It has 2 or 8 electrons in it. The species itself is charged, and to go along with that it has to have a counter ion. We can't magically make an electron disappear, much as we might like to sometimes. It has to go somewhere. And in this type of pair of reactions, where a group 1 element loses an electron, then it has to be in conjunction with something that will gain that electron. And in this particular example, we've chosen group 17 to show that an atom of a group 17 element will gain an electron. It has 7 valence electrons. Gaining that one gives it 8, a filled shell, and the 2 species have to cooperate. They have to coexist. We need to have balance. And we can, again, back to the periodic table, look at general trends in the periodic table. We can say that if we take this general trend from top right to bottom left, as we head in that direction, elements are more likely to lose electrons to form positive ions. And we can reverse the trend by saying if we go from the bottom left towards the top right, in general, in the direction of the arrow, elements will tend to gain an electron and form a negatively charged ion. So we can kind of predict what we think is going to happen. If we know nothing about an element somewhere in the periodic table, we can think about it in terms of these trends, and we can make an educated guess as to whether in a compound that particular element or atoms of that element will lose an electron to form a positively charged ion, will gain an electron to form a negatively charged ion, or may be more likely to share electrons to form covalent compounds. It's not a perfect tool, but it does give us an indication of what's most likely to happen in specific cases involving specific elements. For ionic compounds in particular, we needed to have in these substances a balance of charges. So where we have a mismatch in individual charges on atoms of different element types, then we need specific numbers of each type to make up the numbers, so to speak, to give us a balance. So a positively charged ion with M charges, where M is a whole positive number, and Y, our negative ion, where N again is a whole positive number. The formula will be a consequence of cross-multiplying these numbers to tell us the number of each ion type in that formula that gives us an electrically neutral compound. Charges must balance. Covalent compounds are achieved by the sharing of pairs of electrons, and this is where Lewis's dot notation comes in handy, because we can describe the contributions made by each atom to a covalent compound. And we can show that it must be a sensible compound, that it probably does exist, if we can demonstrate that the bonds make sense. So methane, a simple example, each hydrogen sees itself, and I use C in the most loose way, sees itself as having 2 electrons because it has its own electron and it shares another electron from carbon. And all 4 hydrogens do that. Carbon has 4 valence electrons naturally. In order to achieve its octet, it shares 4 electrons, 1 from each of the hydrogens. So it sees itself as having a filled valence shell. All the atoms are happy. They think they've got what they want to achieve in forming a compound, a filled valence shell, and as a consequence, we have a covalent compound. We normally describe our bonding in a covalent compound with a single line representing a shared pair of electrons. Where we have more than 2 electrons shared, in the case of molecular oxygen, we have 4 electrons shared between the 2 nuclei. We describe each pair with an individual line. So we draw 2 lines to show a double bond, a sharing of 4 electrons. So if we want to describe what's going on during a particular chemical transformation or process, we do it by writing a balanced equation. We write our reactants to the left, our products to the right, and an arrow connecting them, showing the direction in which the chemical reaction has taken place. In writing a balanced equation, we must obey the law of conservation of mass. We can't magically make atoms vanish to suit our purposes, and we can't magically make them reappear, or new ones appear to suit our purposes. I did point out to you that when we are describing more complicated chemical reactions, such as some of the ones we talked about in organic chemistry, then it's not really feasible to describe where every single atom goes, because these reactions tend to be very complicated and they tend to form a very large number of products, most of which will be in very small amounts and are considered to be contaminants to the main chemical reaction that's taking place. So we kind of break this rule a bit when we're talking about organic chemistry. We show the main products that are formed rather than every single possible thing that could be formed, because if we tried to do that it would be extremely confusing. So this rule gets kind of broken a bit. Organic chemists are like that. They're rebels. They like to break the rules. But in the kinds of chemical reactions we talked about in the first half of the module, a balanced equation is absolutely essential. Just some examples. What this tells us is not only how much of each substance we need to have in terms of moles in order to get a complete chemical reaction, but it tells us the stoichiometric relationship between reactants and products. So if we have 2 moles of sodium and react it with sufficient chlorine, we'll get 2 moles of sodium chloride. That kind of thing. And this becomes particularly important when we start to look at tetrametric analysis, where we have things like this going on, an acid and a carbonate reacting to form specific compounds, a salt, carbon dioxide and water. We need to know the stoichiometric relationship between the acid and the carbonate, and we need to know the relationship between these and the product formed, so we can write down the correct number of moles. It tells us some important things, how much we need to react, and it tells us how much of each individual product we get. So if we are carrying out this reaction to get a specific amount of carbon dioxide, we can then calculate exactly how much acid and exactly how much carbonate we require to give us that specific amount of carbon dioxide. And we can't do it unless we have our properly balanced equation. It's all well and good writing stuff down on a piece of paper. If you want to go and get your hands dirty in the lab, then you've got to have some way of measuring the amounts of things that you want to react together. And we discovered that there's a process for doing this. Rather than counting the number of atoms or molecules we need, then we weigh them. So if we're going to weigh them, we need some common point of reference that allows us to weigh amounts that represent real values, or weigh weights that give us exact, or as close as we can, exact numbers of atoms or molecules. And we do this through Avogadro's number and the concept of the mole. So Avogadro's number is a very big number, and it tells us how many formula units we have in a thing called a mole. And that mole then becomes a universal concept that we can apply to any chemical substance, and as a consequence we can know, if we know the number of moles, how many atoms or molecules of that substance that we have. But we need a standardised definition of the mole, and the one that's been chosen is this one here. 1 mole of any element or compound has the same number of formula units as there are atoms in 12 grams of carbon-12, a particular isotope. If you recall, mass numbers tend not to be whole numbers. Because, what was I going to say? They tend not to be whole numbers simply because we have isotopes of different elements in varying amounts. Trying to think off the top of my head. Chlorine, for example, about 75% of all chlorine atoms are what we call chlorine 35. That is, its total number of neutrons and protons adds up to 35, and about 25% are atoms of chlorine 37, where there are 2 more neutrons. It's still the same number of protons, but 2 more neutrons. So when we work out atomic numbers, we work out mass numbers, we need to take into consideration the number of isotopes there are and the relative proportions of them. Off the top of my head, the mass number for chlorine is 35.45, reflecting the proportions of chlorine 35 and chlorine 37. But nevertheless, this definition of the mole holds true. Formula masses are just the sum of the atomic masses, and the relationship between mass, moles and formula mass can be described with this triangular relationship. I'm sure you're all familiar with it. And if we know 2 of the parameters in this relationship, then we can calculate the third quite easily. We often work in solution. It's often the best way we can get our 2 reactants or 3 reactants or however many reactants to interact with each other is to do them in some sort of fluid medium that allows each type of reacting species to get at the others so that reactions can take place. Particularly ionic type reactions, a liquid medium is the best, so we need a way in which we can describe the amounts of substance in a volume of that liquid. And we use molarity as the way of describing that, as our universal definition of a solution's concentration. And it is the number of moles per litre, number of moles of solute per litre of solution. Units are moles per litre. And however much of a substance we have in whatever volume we have, we can still calculate it in terms of moles per litre. So we have a universal way of describing solution concentration. This is particularly important when we're trying to do these sorts of calculations based on tetrametric analysis, where we need to have a balanced equation. We need to understand the stoichiometric relationship between our reactants A and B in that balanced equation. And we know that if we can calculate the actual number of moles of each substance A and B that we have, then the ratio of those actual number of moles has got to be equal to the stoichiometric ratio, x over y. And we can then use that in a condensed format, and we can work out the concentration of an unknown solution. We can work out the volume of a particular solution we need in order to affect a complete chemical reaction, simply by substituting values into this equation and rearranging as necessary. A very good equation to commit to memory. It's a very important one, and one that will probably be with you for the rest of your careers in this university. Okay? We talked about intermolecular forces and why stuff sticks together, and why it doesn't spontaneously fall apart, why individual molecules will be attracted to other individual molecules, and we invoked this idea of electronegativity. Again, we looked at it in terms of the periodic table, and our trend in electronegativity was from bottom left to top right. That is, those that are closer to the top right of the periodic table are those elements that are more likely to attract electron density towards themselves. This has a consequence. If the differences in electronegativity can be measured, then we can make predictions about the type of chemical compound we have. So where there is a very small difference between two atoms, then we are likely to have what we call a non-polar covalent bond between the substances, hydrogen in this example. Where there is a greater difference, such as in hydrogen chloride, chlorine being a lot more electronegative than hydrogen, chlorine will draw electron density towards itself, creating polarity, creating a small partial negative charge on the chlorine end of the molecule, and as a consequence a small partial positive charge on the hydrogen end of the molecule. We describe those compounds as polar covalent compounds. And where the electronegativity difference is quite large, then we get an actual transfer of electrons, and we get ionic substances formed. Sodium and chlorine are the example in this one. Sodium will lose its electron, chlorine will gain it, and we get an ionic compound formed as a consequence. And we use some of these ideas to describe and predict the sorts of intermolecular forces that we're likely to see. And leaving ionic compounds aside, if we just consider covalent compounds, then the principal ways in which molecules arrange the charge around themselves in order to be attractive or repel other molecules come down to these three basic types: dipolar interactions, hydrogen bonding, and dispersion forces. They all have their part to play. Dispersion forces tend to be with us all the time. It tends to be a relatively weak force, but its strength is to some extent reliant on the molecule itself. Large molecules will tend to have stronger dispersion forces between them than small molecules, for example. Molecules that have a shape that allow themselves to line up with their neighbours will have stronger dispersion forces than bulkier, misshapen ones that can't line up so well. We also talked about electrons. We talked about them in a bit more detail in terms of how we can, or how it has been worked out where electrons actually are in an atom. In a nucleus it's easy. It's that bit there in the middle. That's where all the stuff in the nucleus lives. Electrons tend to orbit. And a lot of work has been done over many decades to try and figure out what we can actually say about electrons and their relative positions within atoms. As part of that, we discovered that electrons have wave-like properties as well as particle-like properties. And so we can invoke these ideas of wavelength and frequency and apply them to particles such as electrons. And we can work out the energy of a particular electron. But what's more important is we can work out the changes in energy when an electron leaves one place in an atom and goes somewhere else. It led us to this idea of atomic spectroscopy, where we could shine light onto a particular collection of atoms of an element, and some light will be absorbed. What light is absorbed is dependent on the energy of that light, and the energy absorbed is dependent on the transitions electrons make within atoms. A certain amount of energy has to be absorbed by an electron for it to move to a new place. And conversely, if you allow that atom to then relax and the electron go back to its original position, an amount of energy is released. That's the same as the amount of energy absorbed, or is of the same wavelength. It's why we see coloured spectra. It's why we see things like our streetlights, where there are sodium streetlights. We see that as intense orange colour, because that is the wavelength of light that's emitted when electrons relax in a sodium atom back down to their ground state. We also talked about the three-dimensional shape that orbitals can have, which is quite important because we then used that to go on and describe some other concepts such as VSEPR theory, which allowed us to understand better the three-dimensional shape of molecules and why they adopt a particular three-dimensional configuration. So we knew that the orbitals exist, and we know they exist in different places because they have different energies, and we group them together in subshells and shells. So we have ways in which we can describe the physical locations. And I'm being very loose in my terminology again. We don't actually know where electrons are. All the work that's been done has been mostly theoretical. It has been substantiated by experiment. But what we can say, and I think I said it in the last slide, is that we have probability distributions. The most likely place statistically that we're going to find an electron of a particular type. That is the type of orbital it's likely to reside in. So in developing these ideas, we had to have a way in which we could describe our electrons. And we don't trivialise it by calling them Bob and Jim. We give them quantum numbers that describes where they live in the atom. Principal quantum number tells us the shell they're in. Secondary quantum number tells us the subshell of that shell. The third, the magnetic quantum number, tells us the subshell of the shell. So we're drilling down into it and describing them in greater and greater detail as we go along. And finally, because we can't have two electrons in an atom with the same set of quantum numbers, and each orbital holds two electrons, we need to differentiate between those two electrons, and we do so with the spin quantum number. One electron in an orbital will have one value, the other will have the other value. So we can tell them apart. In most cases this is not particularly necessary, but we did discover that it was quite important when we invoked the idea of hybridization. We needed to individualize our electrons so we could put them into a new set of hybridized orbitals that allowed us, for example, to explain the three-dimensional shape of carbon-based molecules, their tetrahedron. And it's this idea that allowed us to get there. The numbers of orbitals and subshells are dictated by the value of the shell itself. The smaller the principal quantum number, the smaller the shell, the closer it is to the nucleus, the less space it has to occupy. And as a consequence, it can hold fewer electrons. As we move further away from the nucleus, our shells occupy greater areas or volumes, and as a consequence, there are more subshells allowed the further away we get. And as a consequence of that, the more orbitals we are allowed in these subshells, in these shells that are further away, and so we can hold more electrons. So it explains why, as we travel along a period in the periodic table, that we now have a way in which we can describe where the electrons go. It's no longer as simple as saying, well, it increases by one proton, so it's a atomic number has changed. We can also start to say, well, now it has another subshell of electrons, because we need it to hold the electrons we now have. And as a consequence of that, we can start saying things about the properties of the reactivity, in terms of what electrons are available to react, and some of the physical properties in terms of what three-dimensional shaped molecules can have if they have these particular electrons in valence shells that are further away from the nucleus. And that's kind of captured in this diagram. We can describe elements in a number of ways. We can describe them with their symbol and their atomic number to tell us what they are. We can also describe the electron configuration, so we can understand which ones are the valence shells and which ones are going to be involved in chemical reactivity. And we can also just describe them as filling up. Valence shells, or the next shell out, one at a time before they pair up. And this allows us then to invoke ideas about chemical bonding. How many do we have available to form bonds? And where we don't find enough, then we can start to think about this idea of hybridization. How we can demonstrate that there are, in fact, sufficient orbitals available to form the required number of bonds for a particular chemical substance. And if we don't know anything about this, then we can't work out anything about this, and we can't understand hybridization. And we're going to struggle understanding large-scale macromolecular properties. Okay? So that's kind of all there was really that I wanted to get you to think more deeply about from the first part of the semester. And similarly in the second part of the semester, when I started talking about organic chemistry, I introduced you to a lot of things in the hope that you would engage with it and make a good effort to understand it. Some of the things that I introduced you to are important within the context of this module. Everything I've told you is important in the context of your program. So while lots of information such as conformational analysis that I did last week, it was there to introduce you to the ideas behind it, rather than to make you learn everything there is to know about it, because I'm going to come back to these ideas next semester. They're quite important in helping us to understand the interactions that take place within molecules and between molecules that allow us to say something about the three-dimensional shape and properties of these molecules. So anyway, hydrocarbons. We looked at simple ones, alkanes, and we discovered that they're not so simple as we thought, that as we have more carbon atoms in our alkane, and as a consequence more hydrogen atoms, then they can start to be rearranged in all sorts of interesting ways. And we discovered that the more carbon atoms there are, the more possibilities there are for larger numbers of what we call isomers, things with the same molecular formula but are arranged three-dimensionally in different ways. That is, the order in which the bonds are connected together differs. And before too long, we're up into the thousands. 14 carbon atoms, not very many, but 1,800 possible ways of arranging these atoms joined up together. Quite spectacular, really. And it gives us a bit of insight to the range and scope of organic chemistry and the possibility for, theoretically, an infinite number of organic molecules, all based on a carbon skeleton, but with other things involved as well, atoms of other elemental types, such as nitrogen, oxygen, sulfur, phosphorus, arsenic, to name but a few. And we just talked a bit about the naming. I'm not going to go through all the naming rules with you again, but for the isomeric forms of C6H14, then we can have these 5 isomeric forms. We can draw them in these ways, and this is a shorthand where we are implying that the end of a line and the junction between 2 or more lines represents a carbon atom, and hydrogens are just implied. We know that each of these carbon atoms must have 4 bonds, and if we chose to, we could write down the number of hydrogens in our structure to represent that. But the bottom line is that we have different names for them because they're joined up differently. And we look for the longest continuous chain of carbon atoms, which won't always necessarily be written down in a straight line. So we have to go looking for it. We identify where there are branches in that chain, what is attached to the chain at those branches, and we name the things that are attached to the chain, and we organise the name in such a way that we show not only the name of the thing that's attached at a branch, but its position on the main chain. And we develop a numbering system that gives us the lowest possible set of numbers. All quite straightforward, all lots of fun. We introduced ourselves to this idea that we can have circles of atoms, cycloalkanes. And where we have something attached to a cycloalkane, then we can develop a system that allows us to name that molecule properly. Where there is one thing, it becomes the name of the cycloalkane and the name of the substituent joined together. Where we have 2 or more things, then we number them relative to each other. We don't say that that particular carbon atom is carbon 1. We just look to see where the groups are, and we say that in terms of the lowest numbering system, they are in positions 1 and 3 with respect to each other. And for more complicated ones, we do the same thing. We look for ways in which we can develop a sensible set of numbers that are the lowest set of numbers we can develop. And just to reinforce the idea that direction doesn't matter, it's relative position, we can draw that dimethyl cyclohexane any way we want. And as long as our 2 methyl substituents are in the relative positions 1 and 3, then it's always going to be the same molecule, however it's written down. We also introduced ourselves to this interesting idea that came back a number of times, this idea that we can have a classification of atoms within a structure. And this one is representing the carbon atoms and their classifications, and we classify them by looking to see what they're attached to. So a primary carbon atom in this particular structure will be one that's attached to only one other carbon atom. A secondary will be attached to 2 other carbon atoms, tertiary attached to 3, and quaternary is a carbon in the structure that's attached to 4 other carbon atoms. And this became quite important to us when we started looking to explain particular chemical reactions. And not only explain chemical reactions, but also predict the outcome of chemical reactions that we may never have seen before. If we understand that these classifications tell us something about the chemical reactivity of particular, in this case, carbon atoms, then we can understand and predict what's going on in reactions we may never have seen before. Properties of alkanes: combustion, most important one. It's what gives us power. We generate most of our electricity in this way. We heat our homes in this way, cook our food in this way. It's an important reaction. It's also lots of fun setting fire stuff, and there can be consequences, of course, if we get it wrong. If we have, in this example, insufficient oxygen present to react stoichiometrically with all of our alkane, then we are likely to get carbon monoxide formed, a poison. So again, we're back to this idea that if we have a balanced equation, we can understand the stoichiometry of it, and we can make sure that we have sufficient reactants to give us the products that we want, and we're not accidentally making a deadly poison. Oh, I forgot I did this. Halogenation, let's get through it. The other important reaction was halogenation, where we can replace one or more of the hydrogen atoms of an alkane with a halogen, such as chlorine or bromine. They're the ones that are most likely to be used because the other halogens, iodine and fluorine is way too reactive and will just go bang. Iodine reacts so slow that you'll spend the rest of your lives waiting for it. But chlorine and bromine react with alkanes in an exothermic way. They give out some energy, so we don't need to put a lot of energy in to start the chemical reaction, but we need some, and normally it's a bit of heat, or quite often we will do something like shine ultraviolet light onto the chemical reaction. That provides sufficient energy to start the chemical reaction, which becomes self-sustaining until everything's used up. Because these smaller alkanes are gases, we quite often do this in the vapour phase. We'll just mix the gases together, shine light on them, and we get a chemical reaction taking place. What we also discovered was that the more carbon atoms there are, then the more likelihood there is for isomers being formed. And if we use enough bromine in this chemical reaction, we're likely to get some of all of these and many others as well. So the chemical reaction doesn't just stop where we want it to. We have to be careful about how much of our reactants we put into the chemical mixture. So again, stoichiometry is an important concept to apply in this case. But nevertheless, we get lots and lots of different isomers formed. We went on to talk about unsaturated hydrocarbons, alkenes in particular, where we have one or more bond in the structure that we call a double bond, a sharing of 4 electrons between 2 nuclei. And we looked at the ways in which we can describe those particular compounds. We also looked again at a naming convention, and we discovered that what we wanted this time was the longest continuous chain of carbon atoms that contained the double bond. Again, we're looking for branches on the chain. Again, we're naming those things that are attached at the branches, and we're constructing a name for the molecule that gives us the lowest numbering system, that identifies the substituents and where they are, and also tells us the location of the double bond. So it's just the same sort of naming convention, just a little bit more complicated, because we have to take the double bond at its location into consideration. And where we have multiple bonds, we need to say where they are. So we need to give the starting carbon atom for each of the 2 double bonds, and we have to say it's a diene, there's 2 double bonds. We also discovered that these double bonds had a particular property, and that unlike carbon-carbon single bonds, they do not rotate. So a double bond in a molecule introduces an area of rigidity, where the things that are attached to those double bonds don't move, they can't rotate out of the way. I'll get through this. And we discovered that we could describe the relative positions of groups that are attached to the carbons of double bonds by invoking this idea of cis and trans isomerism. We also showed that there's another set of notation we call E and Z. Cis and trans is pretty useful when we're talking about simpler molecules, such as these, which are just alkenes, nothing complicated about them. But where we have different functional groups attached to the carbons of the double bonds, it sometimes becomes better and more transparent to use the E and Z notation to describe the cis and trans concept. And in order to decide what we mean or how we apply cis and trans, we look to see what's attached, and we prioritise them by atomic number of the first atom attached. And obviously carbon has a higher priority in terms of its atomic number than hydrogen. The same here. And the 2 higher priority groups are on what we say is opposite sides of an imaginary plane through the double bond, hence we call it trans. Where we find that the higher priority groups are on the same side of that imaginary plane, we call it cis. And where there are multiple double bonds in the molecule, we have to give a convention to each of them and say where they are. But obviously some we can't apply cis and trans to because they don't have different groups on both carbons. Okay? Cycloalkenes in the same way. Again, what we're doing here in the naming convention is identifying the relative positions. One important caveat we now have a double bond, so the carbon atoms of the double bond will be numbers 1 and 2 in our ring system, and everything else is numbered relative to it. Where there's a choice of ways in which you can number it, pick the one that gives you the lowest set of numbers. For example, in the final example here, if we said that was carbon 1, that was carbon 2, then this becomes our ethyl group on carbon 6, a high number. So by numbering it in the opposite way, 1, 2, 3, we develop a lower set of numbers. We don't necessarily need to say where the double bond is because it's implied by the numbering system. We understand its location because we've numbered other things relative to the double bond and relative to each other. Through this, away. We looked at some of the reactions that are used to form alkenes, and we discovered that where there is potential for competition in the formation of an alkene, particularly in reactions such as dehydrohalogenation, removing a hydrogen halide. So removing this bromine atom together with one of the hydrogens on an adjacent carbon atom, then we've discovered that the tertiary one is more likely to be eliminated because of the nature of the product formed. This particular product is more substituted on the carbons of the double bond than this one is with the 3 hydrogens. So this one, and I think numbers come up, magically they do, this one is going to be formed preferentially. This is a more stable alkene than this one, and is hence the one that's preferred to be formed. So this idea that the classification of, in this case, the hydrogen atoms attached to the carbons is important in that it allows us to explain what we're seeing, and also allows us to predict the outcome of similar chemical reactions. So if you were presented with a molecule that had a primary carbon-hydrogen bond and maybe had a tertiary or a secondary, then the one most likely to be removed with the halogen is the one that's going to give us the most substituted alkene. Generally speaking, that will be the one that's not the primary carbon-hydrogen bond. Okay. We also looked at some properties of alkenes, and we found that there were 2 main chemical reaction types that take place on alkenes, on the alkene group itself. One is the addition reaction, and we discovered there's a whole lot of things that we can add to a double bond to form new chemical compounds. The property that these groups X and Y have to have is that there has to be an electronegativity difference between X and Y. Either X is more negative than Y, or Y is more negative than X. Whichever way around it is, there needs to be an electronegativity difference. The only real exceptions to that are reduction, hydrogenation, but that requires a catalyst to make it work, and also the formation of vicinal dihalides, which is a particular chemical reaction in itself. But generally speaking, where we have X and Y that are of different polarities, then there are rules around what we actually get formed. And it's Markovnikov's rule that governs this. What this tells us is, if there is a choice between orientation, when a hydrogen halide, for example, adds to a double bond, then the product formed will be the one where the hydrogen part of the hydrogen halide attaches itself to the carbon atom on the double bond, which already has the most hydrogens on it. So in terms of hydrogen content, if it's already rich in hydrogens, then it gets even richer after this particular reaction. So 2-bromopropane will be preferentially formed rather than 1-bromopropane, where the bromine atom has attached itself to this carbon with most hydrogens. This is the most likely outcome, Markovnikov's rule. It's important. And I think that's it. I think everything else is stuff that I'd like you to learn. But in terms of what you're going to be doing in 2 weeks' time, this is kind of the headlines. So I'm not telling you what the exam questions are going to be. But I'm suggesting if you pay attention to this one a lot, that you should be alright as far as my stuff's concerned. Can't speak for Graham still. Alright, is that helpful? Alright, leave money at the end of the desk then. Thank you. Right, all I've got to say is the very best of luck in the exam. Root for you, fingers crossed. And I'll see you all next semester for a whole new module and some more fun chemistry. I don't know. There's not an awful lot we can actually do. What we call it to do. It's too late for maybe circumstances like that.
No, I mean, like, obviously you get a case of
Put it in writing. You know what you're doing yourself, just to have a record. So that when it comes to decision making, if we're allowed to take into consideration, we won't take it into consideration. I'm not sure we're allowed to. I do expect you to know